February 15th, 1943. Kummersdorf Proving Ground, 60 kilometers south of Berlin. The morning air hung thick with diesel fumes and mechanical oil, the scent of German engineering prowess that had carried the Wehrmacht across Europe in a series of lightning victories, seemingly validating every assumption about Teutonic technological superiority. Snow crunched beneath jack boots as uniformed technicians moved between the testing bays, their breath forming clouds in the frigid air that carried both the metallic taste of winter and the acrid smell of burnt lubricants from overnight engine tests. Inside Hangar 7, beneath the harsh glare of arc lights that cast sharp shadows across concrete floors, stained with years of hydraulic fluid, transmission oil, and the blood-red liquid that German engineers had learned to associate with mechanical failure, sat an anomaly that would shatter their worldview. An American M4A1 Sherman tank, captured just weeks earlier in the Tunisian desert during the humiliating American defeat at Kasserine Pass. Its olive-drab paint was scarred by Africa Korps shells and sandblasted by the Saharan winds that had blown across North Africa for millennia. The tank bore the name War Daddy 2, stenciled on its turret in the crude block letters American tank crews favored, a sentiment embodying the brash confidence of democratic soldiers who named their war machines like beloved pets, rather than treating them with the respectful fear German crews reserved for their temperamental panthers and tigers. The German engineers surrounding this foreign machine represented not just technical expertise, but the philosophical pinnacle of National Socialist industrial thought. Men like Oberingenieur Heinrich Klaue, chief of captured enemy equipment, analysis and holder of 2 engineering doctorates from the University of Berlin, had spent their careers perfecting the intricate, precise mechanisms that powered German panzers and had come to see mechanical complexity as a reflection of racial superiority. His team included some of Dr. Ferdinand Porsche's most trusted protégés, specialists in advanced metallurgy from the legendary Krupp Works, where steel had been forged for German armies since the Franco-Prussian War, transmission experts who had designed the sophisticated gear systems of the Panther and Tiger tanks, representing the technological culmination of centuries of Germanic engineering tradition, and electrical specialists whose work on fire control systems had pushed the boundaries of precision manufacturing to levels that seemed to approach the limits of human ingenuity. They approached the Sherman with the measured confidence of master craftsmen, examining what they assumed would be a crude apprentice's work. Their careful steps and methodical notations reflected not only decades of engineering training, but generations of cultural belief in German technological supremacy. Their clipboards held standardized evaluation forms developed over years of analyzing captured Soviet equipment, forms that had consistently confirmed German assumptions about the inferior quality of enemy materiel. They expected to find the E-How hallmarks of democratic mass production that Nazi ideology had taught them to recognize. Inferior American metallurgy produced by workers who lacked the generational skills of German craftsmen, sloppy tolerances reflecting the haste and carelessness of capitalist profit-seeking, and the kind of mechanical mediocrity their propaganda ministry assured them was inevitable when quantity was prioritized over quality. What they discovered instead would fundamentally challenge everything they believed about German engineering superiority. It would force them to confront the terrifying possibility that their entire approach to armored warfare was strategically flawed, and ultimately reveal that their understanding of industrial excellence had been fatally corrupted by ideological assumptions bearing no relationship to the realities of mechanized warfare. The Sherman's capture had come during one of the most humiliating defeats in early American military history, a defeat that had initially seemed to confirm every German assumption about American incompetence. Rommel's Africa Korps had overrun elements of the inexperienced 1st Armored Division near Sidi Bou Zid during Operation Frühlingswind, the opening phase of what would become known as the Battle of Kasserine Pass. German forces had advanced with the precision and tactical sophistication that had made them masters of the European battlefields, exploiting American inexperience and poor coordination to achieve a stunning victory that netted hundreds of prisoners and dozens of intact American vehicles. The Shermans had been abandoned not primarily due to enemy fire, but because of mechanical failures and crew inexperience that left serviceable tanks scattered across the desert like mechanical corpses. German recovery teams, accustomed to their own chronic breakdowns, had initially assumed these were simply more examples of the mechanical unreliability that plagued all armored vehicles in desert conditions. The irony of that assumption would soon become devastatingly apparent to everyone involved in the Kummersdorf testing program. German intelligence had already formed preliminary assessments of American armor capabilities based on battlefield observations. From North Africa, interrogation of captured American tank crews, and analysis of technical manuals recovered from destroyed vehicles. These reports painted a reassuring picture of American tanks as numerically superior but technically inferior. Exactly what Nazi racial ideology predicted about democratic mass production versus Germanic craftsmanship. German analysts confidently concluded that the Americans were attempting to compensate for individual tank inferiority through overwhelming material advantage, a strategy that seemed to confirm Nazi theories about the fundamental character differences between races and political systems. The captured Sherman had been selected for detailed analysis not because it represented anything exceptional, but precisely because German intelligence believed it represented typical American armor, average in every respect, and therefore useful for understanding the general characteristics of the equipment they would face as American production ramped up throughout 1943. The tank had been transported to Kummersdorf along with several other captured vehicles, part of a systematic program to understand enemy capabilities. A program that had served German forces well throughout the early war years, when Klaue's team first raised the Sherman's engine compartment using the testing bay's massive hydraulic lift system, itself a product of decades of precision manufacturing. They expected to find the familiar nightmare of over-engineered complexity that increasingly plagued their own armor designs. German engineers had been attempting to squeeze maximum performance from increasingly scarce resources, producing tanks whose engines had become mechanical marvels of precision engineering. Advanced metallurgy, sophisticated fuel injection systems, and complex cooling mechanisms that demanded constant attention from skilled mechanics to function properly. Instead, they discovered something that violated every principle of their engineering philosophy and challenged their fundamental understanding of what mechanical excellence meant. Elegant simplicity that actually worked under the harsh conditions of combat. The Sherman's Chrysler A57 multibank engine, essentially 5 inline 6-cylinder automobile engines arranged radially around a common crankshaft and connected to a single transmission, represented exactly the kind of crude American thinking that German engineers had been taught to despise since their earliest technical education. The A57 multibank was, by German standards, a mechanical absurdity that violated basic principles of engine design. Rather than developing a purpose-built tank engine optimized for armored vehicle requirements, the Americans had simply taken existing automobile engines and combined them in a brute force approach that German engineers found almost insulting in its simplicity. The engine produced 370 horsepower through what appeared to be nothing more sophisticated than mechanical multiplication, rather than the advanced engineering solutions German designers prized. German engineers examined the casting quality with instruments calibrated to detect flaws measured in fractions of millimeters, measured tolerances that seemed impossibly loose by German precision manufacturing standards, and analyzed the metallurgy using spectroscopic equipment that revealed alloy compositions primitive compared to the advanced steel formulations developed by German foundries. The components showed clear evidence of mass production techniques that German industry, geared toward artisanal precision, could barely comprehend or reproduce. Weld seams displayed the characteristic patterns of automated production equipment rather than the hand-finished perfection that German craftsmen took pride in. Machining marks showed tool paths that prioritized speed over surface finish. Even the paint application was purely functional rather than aesthetic, applied by spray systems designed for coverage rather than appearance. To German eyes trained to see precision craftsmanship as the hallmark of true quality, every aspect of the Sherman's construction screamed mass production. Yet as they began their methodical testing protocol, procedures developed by the Heereswaffenamt over years of captured equipment evaluation. This supposedly inferior power plant ran continuously for hours without the constant monitoring and careful nursing that German tank engines demanded to avoid. Catastrophic failure. More disturbing still, when German mechanics deliberately introduced common battlefield damage scenarios, sand contamination in the air filtration system, minor shrapnel damage to cooling lines, partial coolant leaks simulating combat damage. The American engine continued operating at acceptable performance levels. Similar damage would have caused German engines to seize within minutes. The psychological impact on these men, trained from childhood to believe in German technological superiority, cannot be overstated. These were engineers who had designed what they genuinely believed were the mechanical marvels of the modern world. Tanks whose sophisticated transmissions, complex interleaved road wheel suspensions, and precision-machined components represented not just the pinnacle of mechanical engineering achievement, but validation of everything they had been taught about German cultural and racial superiority. The Panther's AK-7-200 transmission was indeed a masterpiece of precision manufacturing, incorporating gear-cutting techniques and metallurgical advances representing years of development by some of Europe's most skilled engineers. Tolerances were measured in fractions of millimeters, the gear profiles mathematically optimized for maximum efficiency and minimum wear. Its lubrication system incorporated advances in hydraulic engineering that pushed the limits of what was technically possible with 1940s manufacturing technology. The Tiger's overlapping road wheel suspension provided genuinely superior cross-country performance through ingenious engineering solutions that distributed the vehicle's enormous weight more effectively than any previous tank design. The interleaved wheels and torsion bar springs represented a sophisticated understanding of mechanical engineering principles, applied with typical German thoroughness and attention to detail. But these same mechanical marvels, these triumphs of Germanic engineering genius, broke down with terrifying regularity, a fact becoming impossible to ignore or explain away as temporary production problems. Panther tanks in frontline combat formations suffered mechanical failure rates that frequently exceeded 50% within their first 100 kilometers of combat operation, rates so high that German commanders had learned to expect half their tanks to be non-operational at any given time, not because of enemy action, but due to mechanical problems. A typical Panzer IV, the backbone of German armored forces, continuously refined since the mid-1930s, required an average of 40 hours of maintenance work for every single hour of combat operation, a ratio that was destroying German armored effectiveness faster than Allied firepower could. Tank crews spent more time with wrenches and oil cans than with ammunition and target identification, while American crews, according to intelligence reports, seemed to spend most of their maintenance time on routine cleaning and inspection rather than emergency repairs. The Tiger tanks, those 60-ton monsters that struck terror into Allied crews when they functioned properly, suffered from final drive units that lasted on average less than 1/500 kilometers before complete failure. These precisely engineered mechanical jewels, manufactured to tolerances demanding specialized tools and highly skilled technicians, would often disintegrate, under combat stress, stranding irreplaceable. Tanks in the middle of battlefields where they became stationary. Pillboxes until ammunition ran out and crews were forced to destroy their own vehicles to prevent capture. German tank crews had developed an almost superstitious relationship with their vehicles that went far beyond normal mechanical sympathy. They performed elaborate maintenance rituals bordering on mechanical mysticism and carried personal lucky charms intended to ward off the mechanical failures that could turn their sophisticated machines into death traps within minutes. Tank commanders routinely spent more mental energy worrying about transmission temperatures, final drive lubrication, and electrical voltage than on enemy tactics or battlefield awareness. The sound of any unusual mechanical noise, a slight change in engine rhythm, an unexpected grinding from the transmission, a new vibration in the suspension, struck genuine terror into German tank crews. They had learned through bitter experience that such sounds often meant immediate mission abort and potentially fatal vulnerability during recovery. Operations required to restore the vehicle to service, yet here, sitting under the harsh fluorescent lighting of Hangar 7 at Kummersdorf, was this crude American tank, built not in a specialized armaments factory by master craftsmen with generations of metalworking expertise, but mass-produced in automobile plants hastily converted from civilian production. These factories were staffed largely by workers who, only months earlier, had been building passenger cars, trucks, and farm equipment, and who had received only basic training in armored vehicle assembly. Willow Run, Henry Ford's massive B-24 bomber plant, partially converted to Sherman production. River Rouge, where Ford had pioneered assembly line techniques, and Chrysler Tank Arsenal, built from scratch in just 18 months, represented an approach to military production that German engineers found almost incomprehensible in both scale and speed. The very idea that complex military equipment could be mass-produced by semi-skilled workers using assembly line methods seemed to violate everything German engineers believed about the specialized knowledge and artisanal skill required for effective weapons manufacturing. The Sherman's components bore unmistakable signs of mass production, techniques that German industry, despite years of wartime pressure to increase output, remained fundamentally unable to adopt without completely restructuring its industrial philosophy. Weld seams displayed the characteristic marks of automated systems rather than the hand finishing that German craftsmen considered essential for structural integrity. Castings bore the slight surface imperfections inevitable in high-volume production, but that would have been rejected as substandard in German foundries. Paint application was clearly functional rather than aesthetic, sprayed for complete coverage and corrosion resistance rather than the flawless finish demanded by German quality standards. Every aspect of the Sherman's construction, from roughly finished internal surfaces that would never be seen in service, to the utilitarian design of access panels and maintenance points, reflected a manufacturing philosophy prioritizing function over form, quantity over individual perfection, and practical effectiveness over theoretical optimization. To German eyes trained to view precision craftsmanship as the hallmark of true quality, the Sherman appeared exactly as Nazi propaganda had led them to expect from democratic mass production. Crude, rushed, and inferior. And yet it worked, with a mechanical reliability that German engineers, despite their sophisticated knowledge and precision manufacturing techniques, had never achieved in their pursuit of individual vehicle perfection. Testing began according to standard Heereswaffenamt procedures, developed and refined over years of captured equipment analysis. The engineers measured the Sherman's armor thickness using precision instruments, respectable at 75 mm on the front glasses, but not exceptional by German standards. They examined its 75 mm M3 L40 gun using ballistic testing equipment capable of measuring muzzle velocity to within a few meters per second. Adequate for most known targets, but hardly revolutionary compared to the high-velocity weapons German engineers had designed. They analyzed its ammunition storage, crew compartment layout, vision systems, communication equipment, and fire control mechanisms using evaluation criteria specifically developed to identify technical advantages and weaknesses that could be exploited in combat. These elements told a familiar story of American pragmatism over German sophistication, confirming initial expectations about democratic, industrial priorities and seeming to validate Nazi assumptions about the inherent limitations of mass production. But when operational testing began, pushing the Sherman through the rigorous protocols designed to evaluate German armor under the harsh conditions of extended combat operations, the American tank revealed its true secret. It had been designed from the ground up to be maintained and operated by ordinary soldiers under battlefield conditions, not by specialists in rear area workshops equipped with precision tools and unlimited time. Every component could be accessed, without the specialized tools required by German tanks, tools that might be lost in battle or unavailable in forward positions where immediate repairs were critical to maintaining combat effectiveness. Engine maintenance required only standard wrenches, screwdrivers, and pliers that any competent mechanic could carry in a basic toolkit. The transmission, while mechanically simpler than the advanced German designs with their precision gear cutting and sophisticated metallurgy, could be serviced by any crew member with basic mechanical knowledge using nothing more than the standardized toolkit that every Sherman carried. Hydraulic systems throughout the vehicle used standardized fittings available across the American military supply chain, easily replaced without special orders or delays. Electrical connections were robust, weatherproof, and designed to function reliably under conditions that would cripple the sensitive electrical systems upon which German tanks increasingly depended, most remarkably to German observers, trained to demand optimal performance from every system. The Sherman could continue to operate effectively even when individual systems partially failed. This design philosophy was alien to German engineering, where every component had to perform at peak efficiency or risk catastrophic failure, requiring immediate withdrawal from combat for extensive repairs. The Americans, it seemed, had built redundancy into their design at every level, accepting weight penalties and additional complexity to ensure continued operation under adverse conditions. This redundancy extended from major systems like the power plant and transmission down to details such as electrical wiring and hydraulic connections, suggesting a design philosophy that expected component failures and prepared for them, rather than attempting to prevent them entirely through extreme precision. Oberingenieur Klaue documented these findings with growing unease in classified reports that would later reveal an engineer grappling with implications that threatened not only his professional assumptions but his entire understanding of what engineering excellence meant in modern warfare. The American tank embodies a type of strategy conceived in terms of mass and material superiority, rather than individual technical excellence, he wrote in his initial assessment. While individually inferior to our vehicles in many technical respects, their operational philosophy appears designed for sustained campaign warfare rather than tactical superiority in individual engagements. This observation struck directly at the heart of German military thinking, which had consistently prioritized tactical excellence over strategic sustainability since the earliest days of Blitzkrieg doctrine. German tanks were engineered like precision instruments designed for specific battlefield roles. Magnificent when functioning at peak performance, capable of destroying multiple enemy vehicles in single engagements, but increasingly fragile under the sustained mechanical abuse of prolonged warfare against enemies with seemingly unlimited replacement capacity. Every German tank represented hundreds of hours of skilled labor by craftsmen whose expertise had been developed over generations. Precision manufacturing techniques that demanded specialized equipment, carefully controlled conditions, and advanced materials that were becoming increasingly scarce as the war dragged on, and Germany's access to strategic resources grew limited. The result was vehicles that were genuinely superior in individual technical capabilities, but could not be produced, maintained, or replaced at rates that matched the demands of global mechanized warfare. The Sherman, by contrast, had been engineered according to principles that German engineers found almost philosophically offensive. It was designed like an agricultural tractor, built to operate under harsh conditions with minimal maintenance, engineered to continue functioning even when many components were operating well below optimal performance levels. This philosophy permeated every aspect of its design, from the robust transmission that sacrificed theoretical efficiency for practical durability to the electrical system that continued to function reliably even when partially damaged in combat. As testing continued through February and into March 1943, with German engineers working in shifts around the clock to complete their analysis before American forces could mount another offensive in North Africa. The psychological pressure on the Kummersdorf team intensified. With each new revelation about American design, philosophy, and manufacturing capability, they discovered that the Sherman's fuel system included an automatic fire suppression mechanism using CO2, cartridges that activated when penetrated by enemy fire, a safety feature entirely absent from German tanks. Despite the horrific crew casualties they had suffered from fuel fires when enemy rounds penetrated German armor, an increasingly common occurrence as Allied anti-tank weapons improved, the result was often catastrophic. Fires that killed crews within seconds and destroyed vehicles that might otherwise have been repairable. The Sherman's automatic fire suppression system, by contrast, flooded the crew compartment with inert gas within moments of penetration, giving American crews precious seconds to escape, time German crews rarely had. This single safety feature made the Sherman significantly safer for its crew than any German tank. Despite its inferior armor by German standards, the Sherman's wet ammunition storage system represented another innovation that astonished German engineers. Artillery shells were stored in glycol-filled containers that absorbed heat and prevented ignition even when penetrated by enemy fire. German engineers calculated that this feature alone reduced crew casualties by an estimated 60% compared to German ammunition storage methods, a statistic deeply unsettling to men who had designed tanks that often became fiery tombs for their crews. Sherman's radio communication system revealed yet another philosophical divide that German engineers struggled to comprehend, one that reflected fundamental differences in how the two nations approached combined arms warfare. While German tank communications remained a chaotic mixture of incompatible systems, different radio types for different units, frequency assignments that changed constantly for security reasons, and equipment requiring specially trained operators, the Sherman carried standardized SCR 508 radio equipment capable of communicating not just with other tanks, but with infantry, artillery observers, close air support controllers, and higher headquarters, all using the same basic procedures. This communications integration revealed a fundamentally different approach to mechanized warfare, one that German observers found both technically impressive and strategically disturbing. The Americans had apparently designed their tanks not as independent weapons to duel other tanks, but as nodes within a broader tactical network integrating armor, infantry, artillery, and air power into coordinated operations that could sustain themselves over long campaigns without the constant micromanagement required by German command structures. Sherman crews, according to captured reports, could call for artillery support using the same radio they used for tank-to-tank communication, coordinate directly with infantry during combined arms operations, and even direct close air support using standardized procedures that required no special training beyond basic radio operation. German tank crews, by contrast, often fought in isolation during critical phases of battle, unable to coordinate effectively. with supporting arms due to incompatible equipment, and overly complex communication protocols that broke down under stress, but perhaps most psychologically devastating to German engineers was the Sherman's electrical system, which embodied everything their own designs had failed to achieve despite years of effort by Europe's best electrical engineers. German tanks had become increasingly dependent on complex electrical networks as designers added advanced fire control systems, powered traverse mechanisms, and communications equipment. But these systems failed with depressing regularity under combat conditions, leaving otherwise formidable machines blind, mute, and helpless. The Panther's sophisticated fire control system, though theoretically superior to anything the Allies possessed and capable of first-round hits at extreme ranges, was notorious for electrical failures that rendered the tank combat ineffective. When the system failed, which it often did due to its sensitivity and the harsh realities of battlefield conditions, the entire tank became useless until specialized technicians could perform repairs requiring tools and parts that were increasingly scarce. The Sherman's electrical system, by contrast, was designed according to principles that German engineers found almost insultingly simple. It was redundant, robust, and specifically engineered for field repair by crew members with only basic technical knowledge. When components failed, and American designers clearly expected them to, the tank remained operational because critical systems had backup power sources and alternate operating modes. Electrical wiring throughout the Sherman was well insulated and routed through protected areas, unlike the exposed wiring common in German tanks that could easily be damaged by shrapnel or rough handling during maintenance. Most astonishingly, Sherman crews could diagnose and repair electrical issues themselves using simple testing equipment and spare parts carried on board, while German tanks often required return to rear area workshops equipped with diagnostic gear and expert technicians. When German electrical systems failed, which happened all too often, tanks became little more than steel coffins. Their crews could no longer see through their advanced but now non-functional optics, communicate with command or nearby units, or operate weapons with the precision German doctrine required. Recovery and repair demanded specialists whose expertise was increasingly rare, and replacement parts that were often unavailable due to Allied bombing and supply disruptions. American tanks, on the other hand, could often be restored to full combat readiness within hours by their own crews. Keeping more vehicles operational and reducing the strain on logistics systems already burdened by global war. The symbol that came to haunt these German engineers was not the Sherman's 75mm gun, respectable but unremarkable by their standards, nor its armor protection, which was adequate but inferior to German specifications. It was something far more mundane, yet ultimately more significant: the standardized toolkit that every Sherman tank carried as basic equipment. Every Sherman, regardless of factory origin or production date, carried an identical set of maintenance tools capable of servicing any part of the vehicle, and compatible with the toolkits of other Shermans in the unit. Wrenches, screwdrivers, gear pullers, pressure gauges, and electrical testing devices were standardized across the entire American armored fleet. This meant that tools lost from one tank could be immediately replaced from another without special ordering or supply delays. German tanks, by contrast, carried specialized tools designed for specific components on particular vehicle variants. When those tools were lost, a common occurrence amid the chaos of battle, recovery operations, or hasty evacuations, even minor repairs became impossible without returning to a rear area workshop equipped with the correct equipment. The Americans had solved this problem with characteristic directness. They designed their tanks so that every system could be serviced using the same basic set of tools, accepting small design compromises to achieve total standardization. This philosophy extended throughout American armored doctrine. As German analysts expanded their study beyond the single captured Sherman, examining technical manuals, spare parts inventories, and maintenance procedures, they realized that American standardization went far deeper than they had imagined. Parts were interchangeable not only within a single vehicle or production run, but across different Sherman variants produced by different manufacturers using varying techniques. A transmission removed from a tank built at Chrysler's Detroit Tank Arsenal could be installed, without modification, in a Sherman manufactured by the Lima Locomotive Works in Ohio. Final drives, road wheels, bogie assemblies, and hundreds of other components were completely interchangeable across the entire Sherman program, regardless of factory, production date, or incremental design changes. German tanks, on the other hand, had become victims of their own obsession with constant improvement, the endless introduction of minor modifications and engineering refinements, each intended to maintain technological superiority over rapidly evolving Allied designs, had produced a logistical nightmare. Each new variant required unique spare parts, specialized maintenance procedures, and retrained mechanics. A Panzer IV, built in 1942, shared relatively few interchangeable parts with one produced in 1944, despite bearing the same designation. The Tiger I and Tiger II, despite their similar names and tactical roles, were completely different vehicles requiring distinct spare parts, maintenance protocols, and specialized training. Even within a single production batch of supposedly identical vehicles, Germany's practice of incorporating running modifications meant that tanks built only weeks apart might require different procedures and incompatible parts. As production dispersed to smaller facilities to evade Allied bombing, quality control became harder to maintain, worsening the problem. The industrial consequences were staggering. American factories could manufacture Sherman components continuously, without halting for retooling, building enormous inventories of standardized parts that simplified logistics across the entire global theater. This consistency eliminated the chronic bottlenecks that plagued German armored units and allowed the U.S. Army to repair or rebuild tanks with remarkable speed. German factories, meanwhile, were constantly forced to retool for new variants and design changes. This created perpetual shortages of spare parts for vehicles already in the field, even as new and increasingly complex models rolled off assembly lines. The result was a paradoxical decline in German armored availability despite stable production numbers. Tanks existed on paper but could not fight because they could not be maintained. By late spring 1943, as German forces prepared for their fateful offensive at Kursk, the final operational reports from Kummersdorf painted a sobering picture, one that German High Command struggled to accept without admitting fundamental errors at the core of their entire war strategy. While German tanks remained tactically superior, boasting heavier armor, more powerful guns, and more sophisticated optics, American tanks were proving strategically superior through operational availability, logistical simplicity, and endurance. A single Panther might destroy 3 or even 4 Shermans in a single engagement. But if that Panther broke down the next day and remained sidelined for weeks awaiting specialized repairs, while the Americans replaced their losses overnight, the strategic advantage clearly belonged to the side that could sustain the fight. The tests revealed an uncomfortable truth. American industrial philosophy had achieved what German engineering never could: a complete, self-sustaining weapon system designed not for short, decisive campaigns, but for total, prolonged war. The Sherman tank was not merely a mechanical creation. It was the material embodiment of American abundance, pragmatism, and democratic efficiency applied to industrialized warfare. Where German engineering sought perfection through complexity, accepting fragility for the sake of theoretical performance, American engineering achieved strength through deliberate simplicity, sacrificing elegance for reliability, and optimizing for persistence rather than perfection. Where German industry exalted the masterpiece, the Americans built the machine that worked, again and again and again. These German engineers, men who had devoted their lives to mechanical perfection, found themselves confronting a philosophical crisis that cut to the core of their professional identity. The Sherman tank had forced them to realize that their pursuit of flawless individual machines had been strategically self-defeating. In seeking the perfect tank, they had built vehicles too complex to sustain in prolonged combat against enemies who valued reliability over refinement. The Americans, with their seemingly crude and unrefined approach, had built an army of machines that could simply keep fighting. While the Germans engineered brilliance that broke down under its own weight, the Americans mass-produced competence that endured, and in total war, endurance was victory.